Chapter 9. Capital Accumulation as a Source of Growth. In this chapter, we introduce the Solow growth model developed by Robert Solow, who was awarded the Nobel Prize for his pioneering contributions to the study of long-run economic growth. The Solow model helps us understand what drives long-run economic growth and what determines differences in the standard of living across countries. Now, let's compare how the Solow model differs from the model we studied earlier in Chapter 3. First, capital K is no longer fixed. In this model, investment adds to the capital stock while depreciation wears it down. Second, labor L is also no longer fixed. Here, we allow for population growth, so the labor force can expand over time. Third, the consumption function is simpler. We won't explicitly model consumption choices as before. Finally, we exclude government spending and taxes simply to keep the model cleaner. However, we can still analyze fiscal policy if needed. In this part, we focus on the production function used in the Solow growth model. We start with the aggregate production function. Y equals a function of K and L. To express output on a per worker basis, we divide both sides by L. So we get lowercase y equals Y over L. And define capital per worker as lowercase k equals K over L. We assume constant returns to scale, meaning that for any scalar z is greater than 0, then zy equals a function of zk and zl. Pick z equals 1 over L, then y over L equals a function of k over L and 1. Thus, we can rewrite the production function as lowercase y equals a function of lowercase k, where a function of lowercase k is output per worker as a function of capital per worker. The slope of this production function represents the marginal product of capital, MPK. So MPK equals a function of lowercase k plus 1 minus a function of lowercase k equals df over d lowercase k equals delta lowercase y over delta lowercase k equals lowercase y2 minus lowercase y1 over lowercase k2 minus lowercase k1. Let's now visualize the production function in a Solow model. On the vertical axis, we have output per worker, lowercase y. On the horizontal axis, we have capital per worker, lowercase k. The curve shows the production function, lowercase y equals a function of lowercase k. The slope of the production function at any point is the marginal product of capital MPK, which measures how much additional output we get when capital per worker increases by 1 unit. Next, we consider the national income identity in this simplified Solow model. Since there is no government spending, output equals the sum of consumption and investment, y equals c plus I. In per worker terms, we divide through by L to get lowercase y equals lowercase c plus lowercase I. This identity tells us that output per worker is allocated between consumption per worker and investment per worker. Now let's introduce how consumption, saving, and investment fit into the Solow model. First, we define the saving rate. Lowercase s is the fraction of income that is saved. It is an exogenous parameter, meaning it is determined outside the model. Important note, lowercase s is the only lowercase variable that is not simply equal to its uppercase version divided by L. The consumption function per worker is lowercase c equals 1 minus lowercase s overall times lowercase y. Let's derive saving and investment. Saving per worker equals income per worker minus consumption per worker, or lowercase y minus lowercase c. Substitute the consumption per worker, then saving per worker equals saving rate times income per worker, or lowercase s times lowercase y. From the national income identity, lowercase y equals lowercase c plus lowercase I. Rearranging gives lowercase I equals lowercase y minus lowercase c equals lowercase s times lowercase y. Substituting from the production function, lowercase y equals a function of lowercase k, we get lowercase I equals lowercase s times lowercase y equals lowercase s times a function of lowercase k. Thus, investment per worker equals a constant fraction saving rate of output per worker. The figure illustrates two key relationships in the Solow model. The upper panel shows the decomposition of output per worker. Output per worker is denoted by lowercase y equals a function of lowercase k. Output is divided into consumption and investment. Then consumption per worker is lowercase c equals 1 minus lowercase s overall times a function of lowercase k, and investment per worker is lowercase I equals lowercase s times a function of lowercase k. The lower panel shows the depreciation function. Depreciation per worker is delta k, where delta is the depreciation rate and k is capital per worker. The depreciation line is linear because depreciation increases proportionally with capital stock. Now let's move to a very important part of the Solow model, capital accumulation. The basic idea here is simple. Investment increases the capital stock, while depreciation reduces it. We can write the change in capital per worker as delta lowercase k equals lowercase I minus delta times lowercase k, where lowercase I is investment per worker, uppercase delta is the change in, lowercase delta is the depreciation rate, and lowercase k is capital per worker. Since investment equals saving and saving is a fraction the saving rate of output, we substitute lowercase I equals lowercase s times a function of lowercase k. Substituting into our equation gives delta lowercase k equals lowercase s times a function of lowercase k minus delta times lowercase k. This equation is known as the equation of motion for capital. It tells us how capital evolves over time. This equation is at the core of the Solow model because once we know how lowercase k changes, we can determine all the other key variables in the economy. For example, let's recall a few important relationships that depend on lowercase k. Income per person or per worker, that is lowercase y equals a function of lowercase k. Consumption per person or per worker, that is lowercase c equals 1 minus lowercase s overall times a function of lowercase k. In short, once we track lowercase k, we can derive output, consumption, investment, and the entire behavior of the economy. Now, let's discuss how the Solow model predicts the economy behaves in the long run. The economy reaches a steady state when the capital stock per worker, lowercase k, no longer changes over time. This occurs when capital accumulation exactly offsets depreciation. Delta lowercase k equals 0. From the capital accumulation equation, delta lowercase k equals lowercase s times a function of lowercase k minus delta times lowercase k. Setting delta lowercase k equals 0, the steady state condition becomes lowercase s times a function of lowercase k star equals delta times lowercase k star, where lowercase k star is the steady state level of capital per worker. In addition, if investment is just enough to cover depreciation, then lowercase I star equals delta times lowercase k star at the steady state level. In the graph, we plot both lowercase s times a function of lowercase k, the investment curve, and delta times lowercase k, the depreciation line, as functions of lowercase k. The steady state occurs where the two curves intersect. At this point, investment equals depreciations. If lowercase k1 is below lowercase k star, then lowercase I1 is greater than delta times lowercase k1, so capital accumulates and lowercase k rises. If lowercase k2 is above lowercase k star, then lowercase I2 is less than delta times lowercase k2, so capital declines and lowercase k falls. Therefore, lowercase k star is a stable equilibrium at lowercase I star equals delta times lowercase k star. Let's work through a concrete example applying the Solow model. We are given with the production function y equals a function of k and l that equals to the square root of k times l, or k take the exponent 1/2 times l take the exponent 1/2. Assume that the saving rate lowercase s equals 0.3 and depreciation rate delta equals 0.1. We are also given with an initial value of capital per worker lowercase k equals 4. The question asks to solve for the steady state values of lowercase k star, lowercase y star, lowercase c star, lowercase I star, and delta times lowercase k star. Step 1. Express the production function in per worker terms. We start by dividing both sides by L, and by following the steps I wrote down, the production function per worker is lowercase y equals lowercase k takes the exponent 1/2. Step 2. Substitute lowercase k equals 4 to compute output per worker. Then lowercase y equals the square root of 4 equals 2. Step 3. Compute consumption per worker. Recall that lowercase c equals 1 minus lowercase s overall times lowercase y. Substitute in values, then lowercase c equals 1.4. Next, compute investment per worker. Investment is given by lowercase I equals lowercase s times lowercase y. Thus, lowercase I equals 0.6. Finally, compute depreciation per worker. Depreciation per worker is delta times lowercase k, then it equals to 0.4. In addition, we like to compute the change in capital stock. The change in capital stock is delta lowercase k equals lowercase I minus delta times lowercase k equals 0.6 minus 0.4 equals 0.2. The conclusion is, since delta lowercase k is 0.2 but not 0, capital stock is still growing and has not yet reached the steady state. Now let's solve for the steady state where the capital stock per worker no longer changes, that is, delta lowercase k equals 0. First, start with the capital accumulation equation. At steady state, lowercase s times a function of lowercase k star minus delta times lowercase k star equals 0. I recommend you try out the steps I've shown here and you will obtain lowercase k star equals lowercase s over delta overall square. Next, plug in parameter values. After plugging in the values of lowercase s and delta, you will find lowercase k star, lowercase c star, lowercase I star, and delta times lowercase k star. You will also observe that lowercase I star equals delta times lowercase k star. In summary, at steady state, capital accumulation has stopped, that is, delta lowercase k equals 0, and all key variables have reached constant long-run values. Here we're going to examine an increase in the saving rate. An increase in the saving rate raises investment. which causes capital per worker, lowercase k, to grow toward a new steady state. In the diagram, when the saving rate increases from lowercase s1 to lowercase s2, the investment curve shifts upward to lowercase s2 times a function of lowercase k. As a result, capital per worker increases over time, moving toward the new steady state lowercase k2 star, where investment again equals depreciation. The key takeaway: the Solow model predicts that countries with higher saving and investment rates will achieve higher levels of capital and income per worker in the long run. In this section, we discuss the golden rule level of capital. Different values of the saving rate lead to different steady states. But how do we know which steady state is the best? The best steady state is the one that maximizes consumption per person or per worker. That is, lowercase c star equals 1 minus lowercase s overall times a function of lowercase k star. An increase in lowercase s has two effects. It raises lowercase k star and lowercase y star, which tends to raise lowercase c star. But it reduces the share of output allocated to consumption, 1 minus lowercase s, which tends to lower lowercase c star. So the question is, how do we find the values of lowercase s and lowercase k star that maximize lowercase c star? Now we introduce the concept of the golden rule level of capital, denoted as lowercase k star goal. This is the steady state level of capital that maximizes consumption per worker in the long run. To find lowercase k star goal, we start by expressing consumption per worker in steady state. Lowercase c star equals lowercase y star minus lowercase I star. That equals to a function of lowercase k star minus lowercase I star. That also equals to a function of lowercase k star minus delta times lowercase k star. Remember that in the steady state, lowercase I star equals delta times lowercase k star because delta lowercase k equals 0. The figure illustrates how consumption, investment, and depreciation relate to capital per worker at the golden rule steady state. The highest vertical distance between a function of lowercase k star and delta times lowercase k star occurs at lowercase k star goal. At this point, consumption per worker lowercase c star goal is maximized. Let's now discuss how the economy transitions to the golden rule steady state. This diagram shows the relationship between steady state output, depreciation, and capital per worker. On the horizontal axis, we have steady state capital per worker, lowercase k star. The green curve represents steady state output, a function of lowercase k star, while the blue line represents steady state depreciation, delta times lowercase k star. The golden rule level of capital is denoted by lowercase k star goal, where the gap between output and depreciation, which equals consumption, that has to be maximized. Below lowercase k star goal, increasing capital raises steady state consumption. However, beyond lowercase k star goal, further increases in capital actually reduce steady state consumption. Consumption is maximized where the slope of the production function equals the slope of the depreciation line, that is, MPK equals delta. Let's summarize the key insight of the golden rule. If the current capital stock, lowercase k star, is below the golden rule level, lowercase k star goal, then increasing lowercase k star will raise steady state consumption, lowercase c star. Conversely, if the current capital stock, lowercase k star, is above the golden rule level, lowercase k star goal, then increasing lowercase k star further will actually reduce steady-state consumption, lowercase c star. The transition process is that achieving the golden rule requires that policymakers adjust the saving rate. This adjustment moves the economy to a new steady state with a higher level of consumption per worker. Let us now examine the adjustment process when the economy begins with too much capital, that is, if lowercase k star is greater than lowercase k star goal. At time t0, policymakers reduce the saving rate in order to move closer to the golden rule steady state. Immediately after the reduction in the saving rate, consumption lowercase c jumps up, investment lowercase I decreases, output lowercase y initially stays the same because capital stock has not yet changed. Over time, capital stock gradually declines. Output lowercase y declines because it depends on capital. Consumption lowercase c eventually stabilizes at a higher level than before the policy change. An important implication: an increase in lowercase c star, which is steady-state consumption per worker, requires a decrease in the saving rate. In other words, to maximize consumption in the long run, sometimes lowering the saving rate can bring the economy closer to the golden rule steady state. In transition toward the golden rule, lowercase c is higher at all points in time. This means that as the economy adjusts toward the golden rule level of capital, consumption per worker increases throughout the entire adjustment process. Next, consider the case when the economy starts with too little capital, that is, if lowercase k star is less than lowercase k star goal. At time t0, the saving rate is increased. Initially, consumption lowercase c falls because a larger share of output is allocated to investment. Investment lowercase I jumps up immediately due to the higher saving rate. Over time, as more capital accumulates, output lowercase y rises. Consumption lowercase c also rises gradually as output increases, eventually reaching a higher steady-state level. This adjustment process allows the economy to move toward the golden rule steady state, where consumption is maximized. The implication is that an increase in steady-state consumption, lowercase c star, requires an increase in the saving rate. Future generation can enjoy higher consumption per worker, but the current generation faces an initial reduction in consumption per worker. Let's go through the quiz questions together. Question number 1. Which of the following production functions has constant returns to scale? I'd like you to try the calculation steps I put here and you'll arrive at the result. A. Y equals K plus L. If we double both K and L, output doubles. This exhibits constant returns to scale. B. Y equals K squared plus L. Doubling inputs does not double output, not constant returns to scale. C. Y equals K squared times L. Output increases more than proportionally when inputs double, not constant returns to scale. D. Y equals K takes the exponent 1/3 times L takes the exponent 1/3. The multiplier 2 take the exponent 2/3 is less than 2. Output increases by less than double, not constant returns to scale. The correct answer is A. Question number 2. An economy without population growth or technological progress has the production function lowercase y equals 20 times lowercase k takes the exponent 1/2. The capital stock is given lowercase k equals 100 and the depreciation rate is delta equals 12%. We are asked what saving rate is required for income lowercase y to grow. First, plug in lowercase k to calculate income or output, that is lowercase y equals 200. Then plug in delta and lowercase k to calculate depreciation, that is delta times lowercase k equals 12. Since lowercase I equals delta times lowercase k, the investment equals the depreciation, that equals 12. Then to calculate the saving rate, we take lowercase s equals lowercase I divided by lowercase y equals 6%. So the saving rate must exceed 6% for income per worker to grow. The correct answer is A. Question number 3. In the steady state of the basic solar model, investment must equal depreciation. So the correct answer is D. Question number 4. In the basic solar model, at the golden rule steady state, the marginal product of capital, MPK, must equal the depreciation rate, delta. So the correct answer is B. Question number 5. If the economy has more capital than in the golden rule steady state, reducing the saving rate will decrease the steady state income and increase the steady state consumption. This corresponds to what we discussed during the experiment shown in the top figure. So the correct answer is C. After all, in this chapter, we explore the solo growth model as a fundamental framework to analyze long-run economic growth. We saw how capital accumulation, saving, and depreciation interact to determine the steady-state level of capital, output, and consumption. The concept of the golden rule helps us identify the optimal level of capital that maximizes consumption per worker in the long run. While higher saving raises capital and output, it may not always increase consumption, highlighting an important trade-off between saving and consumption. Ultimately, the solar model provides important insights into cross-country income differences, long-run growth, and the role of policy in influencing saving and investment.